Any population is characterized by its parameters. If the form of the distribution is known, then the type of parameter is known. A population distribution may be uniform or binomial or Poisson or exponential or normal or any other form. Different populations of the same type will differ in the value of the parameter. The parameters of the population can then be used to obtain the various characteristics of the population that are of interest in economic and business decision making, such as the mean and variance of the distribution. Whatever may be the form of population, as long as the items belonging to the population differ in the value of the variable interest, for example, daily sales of a firm, summary measures like mean and variance of the population values are valuable inputs in the decision making process. There can be many different ways of estimating a parameter of population. Also, estimators have various desirable properties of varying degrees. Therefore, it is desirable to have some general methods that provide estimators with reasonable desirable properties. Here we discuss two such methods, the methods of moment, which is one of the oldest methods, and the method of maximum likelihood. Maximum likelihood estimators are generally preferable to moment estimators, since they yield estimators with certain efficiency properties. However, they generally require significantly large computation than those required by the method of moments. An estimator is a function of sample observation that can be used to reach an estimate of an unknown population parameter value. A good estimator should give as precise an estimate as possible to be useful. If an estimator satisfies desirable properties of unbiasedness and efficiency, it is considered to be the best estimator. If an unbiased estimator is not available, then a consistent estimator may be used. Sample mean is an MVUE of a population mean. Unbiased estimator of population variance is obtained by dividing the sum of squares of deviations of sample observations from the sample means by 1 less than the total number of sample observation. The sample proportion is an unbiased estimator of population proportion. Precision of an estimator is indicated by the standard deviation of the sampling distribution of the estimator. After studying this module, you shall be able to know about the methods of moments, know about the maximum likelihood method. First, we shall discuss the methods of moments. Let a random sample x1, x2 to xn be taken from a probability mass function or probability distribution function. Let exk represent the kth population moment of the distribution fx. We represent the kth sample moment by m dash k, and m dash k is equal to 1 by n summation I from 1 to n xik. Thus, computing by the above method, we get the first population moment as Ex is equal to mu, and the first sample moment is equal to sigma xi by x equal to x bar. Similarly, the second population and sample moments are Ex2 and sigma xi2 by n respectively. The method of moments involves equating the population moments to their corresponding sample moments. Thus, we get as many equations as are required from which we solve for the unknown parameters of the population. The method of moments thus consists of solving the following system of equations: m dash k equal to mu, where k is equal to 1, 2 right up to p for the p parameters of the population. Example 1. If we want to estimate the parameter p of the binomial distribution when n is known, then the system of equations we have to solve is m1 dash equal to mu1 dash. Since mu1 dash is equal to np, so m1 dash is equal to np. Hence p hat is equal to m1 dash divided by n. If both n and p are unknown, then the system of equations we shall have to solve is m1 dash is equal to mu1 dash and m2 dash is equal to mu2 dash. Since mu1 dash is equal to np and mu2 dash is equal to npq plus mu1 dash squared. And solving these two equations for n and p, we get the following estimates of the two parameters of the binomial distribution. M2 dash is equal to M1 dash q plus M1 dash the whole squared, which is equal to M2 dash minus M1 dash into 2 divided by M1, which is equal to q hat, which is equal to 1 minus p hat, which means or implies that p is equal to 1 minus M2 dash minus M1 dash into 2 divided by M1. m1 dash is equal to np, which implies that n hat is equal to m1 dash divided by p hat, which is equal to m1 dash over 1 minus m2 dash minus m1 dash into 2 divided by m1, which is equal to m1 dash into 2 divided by m1 dash minus m2 dash minus m1 dash into 2. Example 2. Given a random sample size 2 from a uniform population with beta equal to 1, use the method of moments to obtain a formula for estimating the parameter alpha. Solution. We solve the equation m1 dash is equal to mu1 dash, where m1 dash is equal to x bar and mu1 dash is equal to alpha plus beta divided by 2, which is equal to alpha plus 1 divided by 2. Thus, x bar is equal to alpha plus 1 divided by 2, and we write the estimate of alpha as alpha hat is equal to 2x bar minus 1. Next, we shall learn about the method of maximum likelihood. In general, let the observed sample values be x1, x2 right up to xn, and P bracket open, capital X1 is equal to small x1, capital X2 is equal to small x2, capital X1 n is equal to small xn bracket close, which is equal to f of x1, x2 to xn, comma theta. Represent the value of the joint probability distribution of the random variables capital X1, X2 right up to Xn at the sample point small x1, x2 right up to Xn. Since the sample values have been observed and are therefore fixed numbers, we regard f of x1, x2, xn, comma theta to be a function of the parameter theta. This function of theta is referred to as the likelihood function and is represented by L theta. Similarly, when the random sample comes from a continuous population of f x1, x2, xn, comma theta is the value of the joint probability density at the sample points x1, x2 to xn. The method of maximum likelihood consists of maximizing the likelihood function with respect to theta, and we refer to the value of theta, which maximizes the likelihood function, as the maximum likelihood estimate of theta. To maximize L theta, which is equal to function of x1, x2, xn, comma theta, we take derivative of L theta with respect to theta and set it equal to 0. The method is capable of generalization. In case there are several parameters, we take the partial derivatives with respect to each parameter, set them equal to 0, and solve the resulting equation simultaneously. Moreover, a large sample drawn from a well-specified population distribution will generate maximum likelihood estimate of the parameter theta having the property of MVUE. That is, it will be approximately unbiased and approximately have least variance. Example 3. Given X successes in N trials, find the maximum likelihood estimator of the parameter theta of the binomial distribution. Solution. To find the value of theta which maximizes, L theta is equal to B bracket open x comma n comma theta, which is equal to nx theta x into 1 minus theta into n minus x. It will be convenient to make use of the fact that the value of theta which maximizes L theta will also maximize L theta, which is equal to log nx plus x log theta plus n minus x into log 1 minus theta. Thus, we get d log L theta d theta, which is equal to x theta minus n minus x 1 minus theta. And equating this derivative to 0 and solving for theta, we find that the likelihood function has a maximum at theta is equal to xn. Hence, the maximum likelihood estimator of the parameter theta of the binomial distribution is theta is equal to xn. Example 4. Suppose that n observations x1, x2 right up to xn are made from a normally distributed population. Find A, the maximum likelihood estimate of the mean if variance is known but mean is unknown. B, the maximum likelihood estimate of the variance if mean is known but variance is unknown. Solution. A. Since f x k mu is equal to 1 divided by root 2 pi sigma squared e raised to the power of minus bracket x k minus mu the whole squared, the whole divided by 2 sigma squared, we have 1 L is equal to f xl mu up to f xn mu, which is equal to 2 pi sigma squared raised to the power of minus n by 2 e raised to the power of minus sigma bracket open xk minus mu the whole square divided by 2 sigma squared. Therefore, 2 in L equal to minus n by 2 log bracket open 2 pi sigma squared minus 1 by 2 sigma squared into summation xk minus mu the whole square. 3. Taking the partial derivatives with respect mu yields 1 by L by del mu is equal to 1 divided by sigma squared summation xk minus mu. 4. Setting del L mu equal to 0 gives xk minus mu equal to 0, that is xk minus n mu equal to 0, or mu is equal to xk. Therefore, the maximum likelihood estimate is the sample mean. Since f bracket open xk sigma squared is equal to 1 divided by square root 2 pi sigma squared e raised to the power of minus bracket open xk minus mu the whole square divided by 2 sigma square, we have L is equal to a function of x1 sigma squared right up to a function of xn sigma squared, which is equal to 2 pi sigma squared raised to the power of minus n divided by 2 e raised to the power of minus sigma in bracket open xk minus mu the whole square divided by 2 sigma square. Therefore, in L is equal to minus n divided by 2 log 2 pi sigma squared minus 1 by 2 sigma squared xk minus mu the whole square. Third, taking the partial derivatives with respect to sigma square yields 1 by L by del sigma squared is equal to minus n divided by 2 sigma squared plus 1 by 2 sigma squared the whole squared into summation xk minus mu the whole squared. Setting del sigma squared equal to 0 gives sigma squared is equal to summation xk minus mu the whole square divided by n. Example 5. Prove that the maximum likelihood estimate of the parameter alpha of a population having density function 2 alpha squared into minus x, comma, where x is greater than 0 and alpha is greater than x for a sample of unit size is 2x, x being the sample value. Show also that the estimate is biased. Solution. Sample of unit size equal to 1. Likelihood function L alpha is equal to 2 divided by alpha squared into alpha minus x is equal to
fx alpha.
log L alpha is equal to log 2 minus log alpha squared plus log alpha minus x, which is equal to log 2 minus 2 log alpha plus log alpha minus x. D by d alpha into alpha, which is equal to minus 2 by alpha plus 1 divided by alpha minus x. D squared by d alpha squared into L alpha is equal to 2 by alpha squared minus 1 by alpha minus x squared. For maxima or minima, d by d alpha should be equal to 0. Therefore, minus 2 by alpha plus 1 by alpha minus x is equal to 0, implying 2 by alpha is equal to 1 divided by alpha minus x, implying 2 alpha minus 2x is equal to alpha, which is moving towards alpha equal to 2x. When alpha is equal to 2x, d squared by d alpha squared into alpha is equal to 2 by 4x squared minus 1 by x squared is equal to minus 1 by 2x squared, which is less than 0. That is, d squared by d alpha squared of L alpha is negative. Therefore, maximum likelihood estimate of alpha is given by alpha hat is equal to 2x. Expected value of alpha is equal to e 2x is equal to 2 integration from 0 to alpha 2x divided by alpha squared into alpha minus x dx is equal to 4 divided by alpha squared into alpha x squared divided by 2 minus x cubed divided by 3, which is equal to 2 by 3 alpha. Since e of alpha hat is not equal to alpha and alpha hat is equal to 2x is not an unbiased estimate of alpha. Let us now summarize what we have learnt in this module. Point estimation refers to the process of estimating a parameter from a probability distribution based on observed data from the distribution. We have discussed two general methods to derive a point estimate for an unknown parameter First is the method of moments and the second is method of maximum likelihood. The method of moments involves equating the population moments to their corresponding sample moments, and the method of maximum likelihood involves estimating those values of the unknown population parameter for which the probability of obtaining the observed random sample is maximum.